When we think about the size of things, we tend to think of the size of things with reference to ourselves. I mean, even the units of measurement that we're familiar with, the foot or the meter, ultimately, historically, they're based on properties of the human body. So they're based on biology. Is the meter, for example, is that something that tells us something deep about the structure of nature? Well, the answer is no. It tells us about biology on Earth, but it doesn't tell you anything profound about the deep structure of the universe. You could imagine if we met some aliens from some different civilization. They might not even have arms, right, or feet, but they might be very different in size and scale from us. So what would the common language be? Is there some unit of measurement that we could all agree on? And so Max Planck came up with a system of units, a way of saying, well, what are the fundamental constants of nature as we understand them? Things that really tell us about the underlying structure of the universe. So one would be the speed of light. It is a property of the universe. Everything that is massless travels at the speed of light, at this speed. And if you have any mass at all, you cannot accelerate to this speed, a universal speed limit. Another one would be the strength of the gravitational force. So what is the force between two objects of a particular mass? Or in Einstein's theory, how does a particular amount of matter or energy distort the fabric of the universe? The number that tells you about that is Newton's gravitational constant. And then there's Planck's constant itself. There's a fundamental limit on how accurately we can know the position of a particle and the momentum of a particle. You can't know them both with absolute precision. So the uncertainty on the measurement of the position of something multiplied by the uncertainty on the measurement of the momentum of something is always greater than Planck's constant. So it's a fundamental property of the universe. Those three numbers allow you to define some distances, a particular distance called the Planck length. So I could take Planck's constant, multiply it by the strength of gravity, and divide it by the cube of the speed of light, and then take the square root of the whole thing. You'll find it's a length of the dimensions of meters. It's about 10 to the minus 35 meters. But that is a length that we've calculated by measuring the strength of gravity, the speed of light, and Planck's constant. So it would seem it should have something to do with the deep structure of the universe. And indeed, it does. How important is it? So it turns out that the entropy of a black hole, which is the amount of information hidden within it, is equal to the surface area of the event horizon of the black hole in square Planck lengths. But just think about that for a moment. It's telling us that the amount of information stored in a region of space, in this case, a black hole, is equal to the surface area surrounding that region in square Planck lengths. So it does seem that the Planck length is fundamentally important. That's an astonishing result.